Nonlinear smoothers tend to be both resistant to outliers and analytically intractable. The latter property makes them difficult to study, and thus they have received less attention than linear smoothers. An interactive dynamic graphics program provides a natural way for a statistician to investigate the performance of nonlinear smoothers under perturbation of the data. This film shows such a program and also introduces some new methods for assessing the resistance and robustness of nonlinear smoothers. Let us begin by looking at a scatter plot and summarizing the dependence of y on x with a smooth curve. We'll use a Tukey type smoother based on running medians. These data are the total amounts of precipitation falling on the city of Halifax, Canada, during the month of April for the years 1871 to 1970. Here is the result of smoothing the data using the Tukey smoother. How will the curve change if we perturb the data by altering the value of one point? We want to be able to see the perturbed data as well as the original values. Let's look at the effect on the smooth curve of perturbing the data just one point at a time. To do this, we put the program in point mode. The dashed curve is the result of applying the smoother to the original set of data, and the solid curve is the result of applying the smoother to the perturbed set of data. Three measures of the difference between these two curves are printed above the plot. These are the average squared error, the maximum absolute deviation, and the integrated absolute deviation. Their values help the user to assess the effect of the current perturbation on the smooth curve. Let's return the data to their original values and see what happens when we move a different point. Here we see the effect on the curve of moving a small group of points. Notice that the effects are very local. Let's see what effect these perturbations have on the residuals. In the lower half of the window, you can see the residuals from the two fits given above. Note that a fitted smooth curve is superimposed. This curve is computed using the same smoothing algorithm as was used with the data themselves. Here we see that there appears to be no structure left in the residuals, even after perturbing the data. Another way of perturbing the data is to change the values of all points in the dataset by a small amount. This models the effect of rounding or grouping, and in the program is called the wiggle mode. After each point has been changed by a small amount, the smoothing algorithm is applied to the new dataset. The user can control the amount by which the data points are perturbed by selecting the maximum perturbation with the mouse. Here, the maximum perturbation is set to 2% of the range of the y values. Point motion refers to the direction in which variables are to be perturbed. When y only is selected, each point is perturbed in the vertical direction only. Here we see the effect of increasing the magnitude of the perturbation. Although this smoother is quite robust against the movement of a single point, it is much less robust against the kind of perturbation which is exemplified by the wiggle. Repeated interactive use of the wiggle operation raises the question of how one can measure and display the variability of the smoother when the data are repeatedly perturbed by a small amount. The band wiggle operation is one way of addressing this question. It is useful for gaining understanding of a smoother's behavior under this kind of perturbation. Again, we choose the maximum perturbation. The number of wiggles parameter refers to the number of times the wiggle operation will be repeated independently to form a band of replicate smooth curves. Here we choose the number of wiggles to equal 100. So 100 curves will be drawn on the plot. This gives an indication of how much variation there is in the curve under a fixed amount of rounding and grouping. Now we repeat the band wiggle with a smaller maximum perturbation. Note that the width of the band, and hence the variability of the smoother, varies considerably, and that near the left endpoint the smooth curve oscillates between two values, which is not surprising for a median base smoother. Note that even at epsilon equals 2, the band is quite wide. This smoother is not very robust to perturbation of all the points at once. Now we will examine the effects on the smooth curve of varying the parameters of another scatter plot smoother. This smoother is a one-step M-type smoother which consists of a kernel estimator plus a non-linear correction term. It has two parameters: the bandwidth, which is just the window size of the kernel function, and the cutoff point, which is the fraction of the range of the residuals beyond which points are downweighted in computing the correction term. These data are the final marks in French and mathematics, both rescaled, of 445 high school students in a French-speaking area of Canada. Here we see how the shape of the fitted curve changes as we vary the bandwidth. Notice that even as we increase the bandwidth, there remains a persistent curvature in the smoother. This turns out to be so because these points are the marks of 50 exchange students from an English-speaking area of Canada. They're bright students, as we can see from their high marks in mathematics, but since they were English-speaking, their marks in French were not up to their usual standards. Now we see that changing the cutoff value alters the smoother's resistance to outliers considerably. Use of the program in this way can enhance the statistician's understanding of a smoother's behavior under various settings of the parameters. If one considers a mark to be a measure of a student's knowledge, then both x and y here are measured with error. Thus, it is of interest to ask how the curve which describes the relationship between them changes when all the points are perturbed in both directions simultaneously. One of the most useful applications of the program is that it enables a user to compare several different smoothing algorithms applied to the same set of data. We will compare Friedman and Stutzel's super smoother and Cleveland's Loess with the running M smoother. How different are the three graphs when the same point is moved by the same amount in each graph? Let's compare just two of these smoothers, Super Smoother and Lowest. The span for Super Smoother is chosen locally by the algorithm itself. Note that the curve is strongly affected by the points at lower right. This is not true for the lowest curve. The two smoothers respond quite differently to the movement of an individual point. How does their behavior compare under the band wiggle operation? Now we do it again with a smaller maximum perturbation. The Smoothers workbench and the ideas introduced in it show how dynamic graphics can be a useful tool, not only for data analysis, where it has been in use for some time in systems like Prim9 and the Data Viewer, but also for the evaluation and comparison of statistical methods themselves.